Here's your antisets. You can pause the video to give it a try, and then when you unpause, it'll be me working through the answers. Okay, we're going to start by graphing this. We can tell it's an ellipse because we're using cosine and sine. And the amplitude of cosine and sine is going to tell me my semi-major, semi-minor axes. So x is going to go between 5 and -5. So I can just label this as 5, 0 and -5, 0. And then y is going to go between 3 and -3. So I can label this as 0, 3, and this is 0, -3, -3. Okay, so then I just have to draw an ellipse through those points. Okay, and there's my ellipse. So now determine dx dt, dy dt, and dy dx. So first, for dx dt, I'm going to take the derivative of x, obviously, with respect to t. So just to introduce some new notation here, I can also call this x prime. X prime is the same as dx dt. So x prime is going to be equal to -5 sine t. Derivative of cosine is negative sine. And then y prime is going to be 3 cosine t. So then dy dx, in this case, is going to be y prime over x prime, right? dy t over dx dt. So we get 3 cosine t divided by -5 sine t. That is our dy dx. This determines the slope of our curve. So now to convert to Cartesian form, I need to write cosine squared plus sine squared equals 1. So my first step is to square both x and y. X squared equals 25 cosine squared. Y squared equals 9 sine squared. Okay, so then I need to divide my coefficients. So I get x squared over 25 equals cosine squared. And then I get y squared over 9 equals sine squared. Right? So now I have cosine squared, sine squared. My Pythagorean trig identity says that cosine squared plus sine squared equals 1. So cosine squared, x squared over 25, plus sine squared, y over 9, equals 1. And that is the Cartesian form of my curve. Here are all those answers one more time. There's the graph from Desmos, nicer than I can draw it. And our dx dt and our dy dt, determining our final dy dx. And then here's the Cartesian form of the curve. So hyperbolic curves, what is dy dx for a hyperbola? So we know this is a hyperbola because we're using secant and tangent. So these, I'm just going to tell you these. I will always give them to you. I mean, in this case, it's not like you're taking closed note assessments anyway, but for now I'm going to always tell you dx dt. The derivative of secant is secant tangent. So d dt of just normal secant is secant t tangent t. So then the derivative of 5 secant is 5 secant tangent. And d dt derivative with respect to t of tangent t is going to be secant squared. So then the derivative of 3 tangents is 3 secant squared. So then what is dy dx? Well, we know that we're going to take dy dt and divide it by dx dt. So we have dy dx equals 3 secant squared t divided by 5 secant t tangent t. But because there is a secant on bottom and there's a secant on top, we can cancel the common factor. So we can cancel one of these secants, with this one secant down here, which just leaves us with 3 secant t over 5 tangent t. 3 secant t over 5 tangent t is going to reduce to 3/5 cosecant t. So I'll show you how to do that right now. So secant, another way of writing that, is 3 divided by cosine. Because cosine is the reciprocal of secant, so taking a cosine and putting it in the denominator is equivalent to having a secant in the numerator. And we're going to divide that by 5 sine over cosine, because tangents equals sine over cosine. So then, to divide fractions, I take the numerator, 3 over cosine t, and I multiply by the reciprocal of the denominator, which is going to be cosine t, over 5 sine t. So then we see we have some cosines that are going to cancel, which gives us 3 over 5 sine t. But sine is just the reciprocal of cosecant, so we can write this now as 3/5 cosecant t, with cosecant moving to the numerator, because having cosecant in the numerator is the same as having a sine in the denominator. These are equivalent. So I can now write my dy dx of my hyperbola as 3/5 cosecant t. And this is going to help us understand the behavior of the hyperbola as the point moves, because we're going to look at how the slope is affected and where this 3/5 comes in. So you don't need to be able to graph cosecant, but this is what the graph looks like, and I want to give you some graphical context here, because 3/5 cosecant t is determining the slope of this hyperbola. So we can see that the slope starts up at infinity, and I erased all those words because they were hard to follow and nonsense. So what we have is we can see around t equals 0, that slope is big. We'll say that that slope starts as being infinity. And then obviously as time goes on, where this graph is going down here, and we see that the slope is going to hit a minimum of 3/5, because that's what this point is right here. It's a y value of 3/5. So down here, we have a slope of 3/5. And then as we continue up, that slope goes back up to infinity. So that's like over here. We go back to a slope of infinity. So that's what's happening, right? We go from a slope of infinity to a slope of 3/5 to a slope of infinity again, okay? And then it hops down to a slope of negative infinity, a slope of negative 3/5, and then a slope of negative infinity again. So let's compare this. So this is the graph of slope, right? This is representing the actual slope of the curve. So let's actually look at the curve itself and see how it connects to this graph. So here is the slope of the curve. We're starting, or here is the curve. We're starting right here, where we have a tangent line that is vertical, meaning that we have an infinite slope. Okay, so the point starts, where the point starts, its path has an infinite slope because it's a vertical tangent. But then the point goes off like this, and it's approaching this line. And what do you think the slope of that line is? The slope of that line is 3/5. So what's happening is we start at infinity, we're approaching a slope of 3/5. Okay, then the point hops down here where the slope is still 3/5, but now where is it going? It's going from 3/5 back to an infinite slope. So it starts at infinity, it goes down to 3/5 as a slope of 3/5, and then it goes back to infinity. Infinity, 3/5, 3/5, back to infinity. Okay, now it's approaching this slope. What do you think the slope of that line is? Well, it's just negative 3/5, right? This is positive 3/5, this is negative 3/5. So now we're approaching a slope of negative 3/5. Okay, and then we're at our slope of negative 3/5, and then we go back to infinity. So what's happening is the slope is cycling between infinity and plus or minus 3/5 as this object moves. And because, that makes sense, because cosecant as a graph cycles between infinity and plus or minus 3/5. So that's why it makes sense that this is representing the slope of this hyperbolic curve. So another hyperbola example, we're going to graph for tangent t to secant t. So we've covered how to graph these, but let's see if you can remember. So first, let's actually determine our dy dt dx dt. Again, the derivative of secant is secant tangent. Derivative of tangent is secant squared, so this is 4 secant squared. So then dy dx is going to be dy dt divided by dx dt. So we just divide them, and we get 2 tangent t over 4 secant t when we divide them, because one of the secants is going to cancel. And then that's going to simplify to sine t over 2. I'll show you how. So we have 2 sine t over cosine t. And we're dividing that by 4 over cosine t, because cosine is the reciprocal of secant. Tangent is sine over cosine. Copy the numerator. We're going to do the numerator multiplied by the reciprocal of the denominator, since we're dividing fractions. Okay, the cosines cancel. And then what are we left with? 2 over 4 sine t. Right? Well, 2 over 4 sine t is just going to simplify to sine t over 2. So dy dx for this curve is sine t over 2. What do we know about sine? Well, sine is a cyclical curve. Sine just goes up and down, up and down, up and down, right? But what is the amplitude of this particular sine graph? It's 1/2, right? This amplitude is 1/2. So that means that we're going to cycle between negative 1/2 and positive 1/2. And since this is representing the slope, we're saying the slope must stay between negative 1/2 and positive 1/2. If you look at this hyperbola, you can see that the slope is 0 here. This is a slope of 0 because we have a horizontal tangent. And then from here, what do we approach? We approach a slope of 1/2. We have a slope of 1/2. We're back to 0. Negative 1/2, negative 1/2, back to 0. Positive 1/2, back to 0. So the slope's just cycling between negative 1/2 and 1/2, never getting bigger than 1/2 or smaller than negative 1/2. And that makes sense because the slope is modeled by sine t over 2, which models that behavior. So now we're starting to get more of a picture of how hyperbolas, like how steep they are. It depends on how we're modeling their dy dx. So now let's connect this back to that weird box thing. So when I graph x of t 5 tangent t, y of t 10 secant t, the fact that secant is y tells me that it opens vertically. So I know that I need to have a point at 0, 10 and 0, negative 10, since the 10 coefficient in front of secant. And then how do I determine the rest of the shape? Well, I have to make this little box thing. So I've already gone up 10, down 10. So then I've told you that what you need to do is you need to go to 0 or 5, 0, which is right here, and negative 5, 0. And then we go ahead and make this little box using those 4 major points, right? And then we use the corners of those boxes to determine the slope, the slope of the asymptotes. So we draw the asymptotes in, and then now we know that our hyperbola has to exist between those asymptotes. But if we connect this to dy dx, okay, well, I know that dy dt is 10 secant t tangent t, and I know that dx dt is 5 secant squared. So then when I divide them to get dy dx, I get 10 secant t tangent t over 5 secant squared. This secant is going to cancel with one of those secants. So then I get 10 tangent t over 5 secant t, which from earlier, go back for a sec, we know that tangent t over secant t just simplifies to sine. That's the work that we did in this previous slide back here. So this simplifies to, this equals just 2, because 10 over 5 is 2, times sine t. So what's true about our slope? Our slope goes between negative 2 and 2, according to this dy dx that we just determined. Okay, so then when I think about this graph, well, how do I determine that slope of 2? Well, I've gone up 10, and I've gone over 5, up 10, right 5 to make this box, right? So then the rise over run of the corner of the slants that we get by going through the corners is going to be 10 over 5, which is 2. So now that's where the slope of 2 is coming from, and why this method makes sense, because it basically ends up allowing us to divide this number by this number to determine that slope. So that's why we make this box.